Hello. In previous three lectures on quantum mechanics, you have learnt about the beauty of quantum mechanics in its introduction, the fundamental principles which the quantum mechanics depends upon, and the postulates of quantum mechanics. In this lecture, we will go through the applications of quantum mechanics, in which the focus will be on particle trapped in potential box, particle encountering potential barrier, and quantum mechanical tunneling. Suppose you have a trolley at this point. As soon as you unhold it, it starts moving and gains kinetic energy, which after passing the valley is used to keep it in motion until the same height as the starting point is reached at this point. From here, it starts moving in reverse direction again, and in this way, it gets trapped in this valley. In similar way, an electron can be trapped in potential configuration. When it happens, it moves toward any potential wall, of course negative, hits it and reverts its direction of motion to hit the another wall. These situations can be shown as this. Here we have three regions. The potential in region 1 and 3 is infinite, while the same in region 2 is 0. Since a potential means the required energy to reach a given region of space, an infinite potential indicates that the particle needs an infinite energy to reach region 1 and region 3, or it cannot be found in infinite potential regions. This problem is known as particle in infinite potential box or particle in infinite square well potential. Mathematically, it can be represented as this. Since particle cannot be found in region 1 and 3, so the wave function in these regions of space does not exist. Our aim is to find the wave function of particle in region 2. This can be done using Schrödinger equation. Wave function in region 2 psi 2 is non-zero. To find it, few necessary conditions will also be followed. These conditions are known as boundary conditions. Now, let us apply Schrödinger equation to find psi 2 in region 2. Here, V is 0. So, the second term of Schrödinger equation becomes 2me by h bar square psi 2x. This is a second order differential equation which is easier to be solved if the factor of the second term is square of some number. Let this number is k, where k is given by this equation. Now the solution can be written in terms of sine and cos of kx. We need to find the values of a, b and k. And for this we will apply few boundary conditions. These boundary value conditions are the following. The vanishing wave function at walls of the well, say psi 2 at x equal to 0 is 0 and psi 2 at x equal to L is equal to 0. And the normalization condition. The limits minus infinite to positive infinite of definite integral can be divided in minus infinity to 0, 0 to L and L to positive infinity. Since this region is the region of psi 1 and this region is the region of psi 3 which vanish, and only the region 0 to L where wave function is psi 2 exists. So this normalization condition reduced to this. Let us apply these conditions one by one on this wave function. The first condition at x equal to 0 gives this, which means b is equal to 0. The second condition at x equal to L gives this, or psi kl equal to sin n pi, which means k is equal to n pi by L, where according to this n can be 0, 1, 2 and so on. If we put this k value and b value in this equation, we find wave function is equal to a sin n pi x by L. Here, if n is equal to 0, then this wave function will not exist. It means there is no particle at all. So to have a valid wave function, n cannot be 0. So n is natural numbers. Since psi depends upon n, we can write psi n equal to a sin n pi x by L. Here, value of a is still unknown. To find this value, let us try the normalization condition which after some mathematical exercise gives a equal to under root of 2 by L, and the whole wave function becomes psi n as a function of x equal to under root of 2 by L sine n pi x by L. The energy of the particle can be found using K like this, and it comes out to be this. We see energy of a particle is different for different values of n. N is known as principal quantum number. Different values of n signify different states of the particle. N equal to 1 is known as ground state of particle, and n greater than 1 are the excited states of the particle. So the particle may have different energies corresponding to different states. The wave function depends upon n, and for different values of n, it can be plotted like this. Similarly, the square of it, which is the probability of finding the particle in a certain region, can be plotted like this. Clearly, the probability of the particle to be at some specific point in potential box is different for different states, like its energies. Let us talk something more about it. Here we see that the wave function for different n values represent different states of the system with quantized energy values. Energy varies with k vector parabolically. K is also known as wave propagation vector. The energy and k vectors are quantized in all the quantum mechanical systems. Let us talk more about why n cannot be equal to 0. N equal to 0 is not expected by Heisenberg's uncertainty principle because it will be violated if a particle has zero energy. The zero energy particle means a particle without motion. Non-zero kinetic energy can be proved as follows. If a particle is confined in a box, then the maximum uncertainty in its position is delta x equal to L, giving the minimum uncertainty in the momentum, or the minimum momentum delta p will be equal to h bar by L, and this leads to a minimum non-zero kinetic energy of the particle, or n is not equal to 0. The non-zero energy reflects the necessity of minimum motion of the particle due to localization. The non-zero energy occurs in all the bound state potentials. The appearance of zero-point energy brings a contrast between classical and quantum mechanics. In classical mechanics, the lowest possible energy is minimum of potential energy with zero kinetic energy, while the quantum mechanics does not minimize the potential energy alone. Rather, quantum mechanics is applied to the sum of kinetic energy and potential energy. The case of bound states where potential is zero lead to a finite ground state energy or the zero point energy. Without zero point motion, atom would not be stable, for the electrons would fall into the nuclei. Also, it is zero point energy which prevents helium from freezing at very low temperatures. Now, let us solve some problems. Let us find the probability of finding a particle. The particle is trapped in box of width L. For this, the wave function has already been found. It is this. The probability can be computed by the formula this. So the probability can be calculated to be like this, or this. The probability is the function of n, indicating that the probability of finding particle depends upon the state in which the particle is at the moment. Now, putting n equal to 1 gives the probability in ground state, and this is equal to 19.3%. You can see it in the figure. It is obvious that the probability for n equal to 2 in this region from x equal to 0.5 L and x equal to 0.4 L is less than this value, which can be found by putting n equal to 2. Indeed, it is 15.1%. Similarly, we can find expectation value of position of particle in the same problem. Now, what do you need for this information? The one is operator, second one is the wave function, and third is the formula for expectation value. On solving, we get the expectation value of position equal to L by 2, irrespective of n. So, no matter in which state the particle is, if you calculate the average position of the particle in the box, it will be the center of the box. Now let us compute the momentum of the particle. For this, let us try the eigenvalue equation. This is a wave function. Let us operate the momentum operator on it to find the eigenvalue like this. But what we see is that given wave function is not the eigenfunction of the momentum operator. So we cannot find the momentum in this way. Now what to do? Let us try to find the expectation value instead. For the expectation value, we have momentum operator, we have wave function and the formula, and by calculation, we get the expectation value of momentum equal to 0. It means the average momentum of the particle is 0. So is this method failed? Let us check it by finding the expectation value by some other method. And we will do it by energy eigenvalues. Since the energy of a particle in nth state is given by this energy can be written in terms of momentum, and by this momentum can be found in terms of energy, and if we put the value of energy En here, we get Pn equal to plus minus n pi h bar by L. Here plus sign shows the values when particle is moving along positive x-axis and minus sign shows the value when movement is in negative x-axis. Since both the values are the same, the average is 0. So there was no failure of the previous method. But what about the eigenvalue of momentum computed by the eigenvalue equation? If the given wave function is not eigenfunction of momentum, then is it possible to find the eigenfunction which when operated by the momentum operator can give the eigenvalue of the momentum? Let us see. Since the momentum operator contains a differential operator and the exponential function is the eigenfunction of differential operator. So if we can write this wave function in terms of exponential wave functions, then it is possible to find an eigen operator. Any sine function can be written as a linear combination of two exponential functions like this or like this. Here, if we write the first part as psi n plus and the second part as psi n minus, then the wave function can be written as the linear combination of two different wave functions. The one represents the wave traveling along positive x-axis, or it represents the particle when it is moving along positive x direction. The second wave function represents the wave traveling along negative direction or a particle when it is moving along negative x-axis. Now the momentum can be found by operating momentum operator on these two wave functions. So the momentum of particle when it moves toward positive x-axis can be found like this, and it will be P plus equal to n pi h bar by L. The same when particle is moving along negative x-axis is this, giving the momentum P minus equal to minus n pi h bar by L, giving the expectation value or average value equal to 0. What we can conclude here is that sometimes the given wave function needs to be modified in order to find the solution. It does not mean that the first wave function is not correct. Both the sinusoidal and exponential forms are correct, but the thing is that we choose the one which is easier to deal mathematically. We'll discuss the other application of particle encountering the potential barrier in next lecture to keep this lecture not too long.